You take the watch at 8 in the evening and the ship is already shaking. Not rolling, not pitching, shaking in a low, continuous shudder that comes up through the deck plates and into your knees, and does not stop for the next 12 hours. Somewhere under the bow, ice 1.5 meters thick is failing, and the noise it makes is not a crack. It is a long, grinding roar with bangs inside it. You will hear that sound until dawn. You will try to sleep through it in 6 hours. Almost nobody manages. And the strangest thing about this ship, the thing that surprises everyone who learns it, is that the bow you are standing above is not cutting anything. It never was. An icebreaker does not slice through ice the way a knife goes through paper. It climbs on top of it and breaks it with its own weight, from above, like a man stepping onto a frozen puddle. That is the beginning of the story and not the interesting part, because breaking the ice turns out to be the easy half of the job. Here is what a night on an icebreaker is actually built around. The ship is 13,000 tons of steel with a hull specifically designed to be terrible at being a ship, because everything that makes it good at ice makes it worse at water. Under the waterline is a belt of plate thicker than your thumb, in some vessels 3 inches of steel, and it exists because the pressure of ice against a hull can reach hundreds of tons per square meter. Behind you, out of sight in the dark, is a convoy of cargo ships following in the channel you are cutting, and they cannot stop. And neither can you, because a channel closes behind a ship in this temperature faster than you would believe. There are 4 things trying to end this night early, and they are not the ones you would guess. The ice does not stop the ship. The broken ice does. The hull is not the vulnerable part. The propellers are. The open sea is not the safe part of the voyage. It is the dangerous part. And the crew is not tired because of the cold. They are tired because of the noise. Before we take over the bridge, subscribe. This channel opens up the machines that make impossible work ordinary. And now let us start with the bow, because almost everything people believe about it is wrong. Look at an icebreaker out of the water, and the first thing that seems wrong is the front of it. There is no point. Where a normal ship has a sharp stem designed to part water, an icebreaker has something closer to the back of a spoon, a broad, gently sloping, rounded surface that meets the water at a shallow angle. Some vessels take it further and are almost square at the bow. It looks blunt, and blunt looks wrong on a ship, and that instinct is the reason so few people understand what is actually happening. The bow is not a cutting tool, it is a ramp. When the ship drives into an ice sheet, that shallow slope does not attempt to split the ice edge on, it slides up over the top of it, and the front of the ship lifts, and now several thousand tons of steel are sitting on a sheet of frozen seawater that was never designed to carry them. And here is a physical property the whole method depends on. Sea ice is enormously strong in compression and remarkably weak in bending. Push against its edge and it will push back with hundreds of tons per square meter. Press down on its surface and it flexes, and then it fails downward in a spreading network of cracks. The bending strength of sea ice is low enough that the ice usually breaks without any noticeable change in the ship's trim at all. The bow lifts a little, the sheet lets go beneath it, and the ship settles forward into the gap it just made. Then it does it again. And again. All night. The analogy everyone reaches for is the right one. Walk out onto a frozen pond and the cracks spread away from your boot in a web. That is not you cutting the ice. That is the ice bending until it cannot, under a load applied from above. An icebreaker is doing exactly that, with the weight of a small building continuously for as long as the ice lasts. It took the industry most of a century to arrive at that shape, and the wrong turn is instructive. Early purpose-built icebreakers followed the intuition everybody has, which is that a wedge is the tool for splitting things. Ships like the original Mackinac carried a comparatively pointed bow, and at the time that represented the best available thinking. It worked. It also had a problem nobody predicted, and it took decades of measurement to characterize properly. A pointed bow drives into a sheet and gets pinched from both sides as the ice closes on it, and that side pressure produces friction, a great deal of it, which the engines then have to overcome on top of the actual braking. The ship was fighting the ice and fighting the ice's grip on itself simultaneously. Modern practice went the other way entirely. Current designs favor a wide, shallow, spoon-shaped bow specifically to reduce that friction, and the resulting shape looks less like a tool and more like an accident of manufacturing. It is the opposite. Everything about it is deliberate. The rake is shallow, so the ship climbs rather than butts. The surface is broad, so the load spreads over enough ice to initiate a wide crack pattern, rather than punching a hole, and the whole thing is rounded so nothing gets gripped, which reframes what the engines are actually for. A Great Lakes Icebreaker of the Mackinac type had propulsion motors delivering something in the order of 7.5 megawatts, around 10,000 horsepower, for the icebreaking job. That is a very large amount of power for a ship of that size, and it is not there to force the ice apart. It is there to keep the hull moving forward so it can keep climbing, and to overcome the friction of everything the hull is dragging itself through. Power buys momentum. Weight does the braking. Confusing the two is the most common misunderstanding about these ships. You take the handover at 8, and the outgoing watch tells you 3 things, none of them about the ice, where the convoy is, which flow they had trouble with 2 hours ago, and how the port healing pump was behaving. Nobody mentions the ice thickness because the ice thickness is on the display, and it is not the interesting variable. So at 8:30 you are watching a sheet of ice 1.5 meters thick fail continuously under the front of your ship, and the ship is winning easily. And in about 40 minutes it is going to stop, and not because the ice got thicker. At 9:20 the ship slows down, and nobody on the bridge is surprised. The ice ahead has not changed. The engines have not changed. What has changed is behind the bow, in the water alongside the hull, where the ice you have already broken is now the problem. A buildup of broken ice in front of and around a ship can slow it down far more than breaking the ice ever did. That is the inversion this whole night runs on, and it is documented plainly in the engineering literature and repeated by everyone who does the job. Breaking the ice is not the hard part. Clearing it is think about what you have actually created. You have taken a continuous solid sheet and converted it into thousands of individual blocks, floating, jammed together, each one wanting to slide back into the space your hull is trying to occupy. That rubble has no bending strength to exploit anymore. You cannot ride up on top of a slush of loose blocks and crush them. They simply move aside and pack tighter. Now you are not breaking ice. You are plowing through gravel that floats, and the resistance is friction rather than fracture. And friction does not fail suddenly the way a sheet does. It just builds. A second officer on one of these ships said something worth repeating. Most people assume snow and ice are slippery. But put 13,000 tons of pressure onto it and you absolutely do get friction. That is the sentence that explains the entire back half of an icebreaker's design. And the weight, which was the tool a moment ago, is now working against you. Displacement is what let the bow break the sheet. Displacement is also what has to be dragged through the rubble afterwards, and there is no way to have one without the other. Icebreakers are built deliberately heavy for their size, heavier than a cargo vessel of the same length, because the weight is the braking tool, and every ton of that advantage becomes a ton of resistance the instant the sheet is finished failing. The ship is designed around a trade-off that reverses on itself several times a minute, all night. There is a second reason the rubble matters, and it is the one the convoy behind you cares about. A channel does not stay open. The blocks you displaced are floating in water at its freezing point, in air at -40, and they begin bonding back together almost immediately, first as slush between the pieces, then as a continuous refrozen crust that a following cargo ship with an ordinary bow and an ordinary hull cannot break at all. The channel behind you is closing while you are still cutting the one in front. This is why escorted convoys hold close station rather than following at a comfortable distance, and why the width of the channel matters as much as the fact of it. A narrow channel closes faster. It is also why an icebreaker cannot simply stop and wait for anything. So the hull is not shaped merely to climb. It is shaped along its entire length to get rid of what the bow just made. The cross-section flares outward above the waterline so that broken blocks are pushed down and outward as the ship advances rather than being trapped alongside. The beam is deliberately wide, wider than a normal ship of the same tonnage, partly to cut a channel broad enough for the convoy behind, and partly so the rubble has somewhere to go that is not underneath you. Every curve below the waterline is answering the question of where the debris ends up, and the reason the debris matters so much is not just that it slows the ship, it is where it can reach, and to understand that you first have to look at what the ship is actually made of. At 10:30 you go down through the ship, and every deck you pass through tells you something about what this hull is expecting. Start at the waterline, because that is where the fight happens. Around the entire circumference of the hull at and just below the waterline runs the ice belt, and it is the thickest steel on the vessel. On a heavy icebreaker, that means plate in the region of 50 to 80 millimeters, 2 to 3 inches of solid steel, where a cargo ship of similar length might carry a fifth of that. On the larger vessels, the belt is not a narrow strip either. Stand next to one in dry dock, and the reinforced band is taller than you are, because the ship does not always meet ice at the same height. It rides up, it settles, it heels, and the ice can press anywhere within that range. The reason for that thickness is a single number. Ice pressing against a hull can generate pressures in the order of hundreds of tons per square meter, and unlike a wave, it does not come and go. It is a sustained, grinding, patient load applied for hours at a time in a direction the ship cannot avoid. So behind the plate, the framing is closer together than on a normal ship. The bottom is double or in places triple, and the whole structure is built to accept a load rather than deflect one. None of this is left to a shipyard's judgment. Classification societies grade ice-capable hulls on a published scale, Polar Class 1 at the top, for a vessel intended to operate year-round in multi-year ice, down through the intermediate classes to Polar Class 7 for light first-year ice in summer only. A Polar Class rating is not a badge. It determines plate thicknesses, frame spacing, propulsion protection, and the ice conditions the vessel is permitted to enter, and it is the first thing anybody asks about a hull before they ask how much power it has. And the hull has a second function that nobody designs for and everybody notices. That flared cross-section above the waterline, the one that pushes broken ice down and outward as the ship advances, is also a hull form with less initial stability than a hard-sided vessel would have. In ice, that flare is a clearing device. In water, it is the reason the ship rolls more readily than its size suggests. The same geometry does both jobs, and one of them is a job nobody wanted, which sets up the thing everybody in the engine control room is actually watching, and it is not the plate. This is the part that reverses most people's mental model a second time. The hull of an icebreaker is extraordinarily strong. A properly built Polar Class 1 hull is simply not what fails. What fails is everything sticking out of it, the external components of the propulsion system. The propellers, the propeller shafts, the rudders are at significantly greater risk of damage than the hull itself. A propeller blade is a precisely shaped piece of bronze or steel, a few centimeters thick at its edge, spinning in water that is full of hard floating blocks the size of furniture. It cannot be armored the way a hull can, because a propeller that is thick enough to be indestructible is a propeller that does not work. Thickness on a blade means drag, and drag on a blade means the ship loses the thrust it needs to keep climbing, which is the one thing it cannot afford. So the blade is left thin, and the problem is solved everywhere else. The shaft has a related and less obvious vulnerability. Where it leaves the hull, it passes through a seal, and a seal is a precision fit between a rotating shaft and a stationary housing, holding back the sea. A blow to a propeller blade does not stay at the blade. It travels up the shaft as a shock load into the bearings and the seal, and a damaged seal in the Arctic is not a repair anybody wants to attempt. The blade is the thing that gets hit. The consequences run inboard. So the entire aft geometry of the ship becomes an exercise in keeping ice away from the one place it cannot be tolerated. That is why the hull is shaped to direct broken ice around the vessel or underneath it, not for efficiency, but to route the debris past the propellers. It is why many icebreakers run their propellers inside protective nozzles, a ring of structure around the blade tips that takes an impact the blade could not. Some older designs went further and mounted additional propellers forward in the bow, both to help clear ice ahead of the ship and to wash the debris out of its own path. And it is why the ability of an icebreaker to climb onto ice, break it, and clear the pieces from its own path is described in the reference literature as essential to its safety rather than to its performance. The clearing is not housekeeping. It is self-preservation. And here is the second function that turns this from a description into something more interesting. The propellers are not only the thing most at risk, they are also one of the tools used to solve the problem. The wash from the propellers can be directed to push broken ice away from the hull and widen the channel, and on ships fitted with rotating pods that can be aimed deliberately. The most vulnerable component on the ship is also part of the ice clearing system. It is protecting itself by working. Modern vessels take that further than most people realize. Azimuth thrusters, pods that rotate a full 360 degrees under the hull, replaced the fixed propeller and rudder arrangement on many icebreakers from the 1990s onward, and they changed what the ship can do. A pod can be turned to flush ice out from alongside. It lets the vessel move astern under full control, which opens a wider channel for the convoy following behind. And it produced a genuinely strange class of ship. The double-acting vessel, which sails bow first through open water and then turns around and breaks heavy ice going backwards, propellers leading, because a pod facing into the ice is a better ice-clearing device than any bow shape yet designed. Which brings us to something the bridge crew has been thinking about all night and you have not, because the hard part of this voyage is not the ice at all. At around 1 in the morning, the conversation on the bridge turns to the weather forecast for the open water at the far end of the passage, and the mood changes. Here is the paradox that governs the design of every icebreaker ever built. Every single feature that makes a hull good in ice makes it worse in water. There is no exception and no way around it, and naval architects have been trading one against the other for a century. The spoon bow is the clearest case. That broad, rounded, shallow-angled front end is the reason the ship can climb onto an ice sheet. It is also the reason the ship is miserable in a sea. A conventional, pointed bow pierces an oncoming wave and lets it pass along the hull, which is most of what makes a ship tolerable in rough water. A rounded icebreaker bow does not pierce anything. The wave hits it flat, at full force, and the ship stops and shudders and throws the water upward instead of parting it. In the Arctic and the Southern Ocean, where 12-meter seas are ordinary rather than exceptional, that means the passage across open water to reach the ice is the roughest part of the voyage, and by some distance the most unpleasant. These are not comfortable vessels on open water, and everybody who sails them says so. The curved cross-section is the same trade. You want the hull curved below the waterline so that ice pressing inward slides rather than crushes, and so that broken blocks are guided away from the propellers. A curved cross-section is also a hull with less form stability and a less kindly motion, which means a ship that rolls more readily in a swell than a hard-chined vessel would. The weight is the same trade again. Heavy is good because weight is the braking tool. Heavy is also more fuel, deeper draft, and more momentum to stop. Even the wide beam is a compromise. It cuts a broad channel and gives rubble somewhere to go, and it costs propulsive efficiency in open water for the entire rest of the voyage. So an icebreaker is not an optimized ship. It is a ship that has been made deliberately bad at 80% of its journey in order to be capable during the other 20%. And the crew crossing open water in one, being thrown around in a hull with no bow to speak of, are paying that bill in advance every time. There is one design that genuinely resolves the paradox rather than trading inside it, and it is worth understanding because it is the strangest ship afloat. The double-acting vessel has two working ends. It has a conventional, reasonably sharp bow at the front for open water, so the crossing is tolerable and the fuel consumption is sensible. Then, when it reaches the ice, it turns around and proceeds stern first with its rotating pods leading, breaking ice going backwards. The stern is shaped for ice. The bow is shaped for water. The ship simply chooses which end to lead with. It sounds like a joke, and it is one of the more elegant pieces of naval architecture of the last 30 years, and it exists only because rotating pods made it possible to put full thrust and full steering at whichever end you want. But most icebreakers are not double-acting, and most of them live inside the compromise. Draft is another line of it. A deep hull carries the weight and the machinery, and a deep hull is exactly what you do not want when the route runs through shallow Arctic shelf water where the charts are old and the bottom is not always where the chart says. Freeboard is another. High sides help in a sea and give the flare somewhere to work, and they also give the wind a great deal to push against when the ship is stationary in a pack and trying not to drift. And every one of these compromises is being lived by somebody at 3 in the morning rather than argued about in a design office. The ship you are standing on is the answer to a question that was settled years ago by people balancing ice capability against everything else a ship has to do, and the crew inherits the balance without a vote. Which is fine, until the moment the 20% stops working, which happens at about 3. At 3 in the morning the ship stops, and this time it does not start again. Nobody panics because this is routine and there is a sequence, but it is worth being clear about what has actually happened, because it is not what most people picture. The ship has not been crushed and it is not in danger. It has simply lost forward momentum and ice too thick or rubble too packed to climb. And an icebreaker without forward momentum cannot break anything, because the entire method depends on driving the bow up onto a surface. Stationary, it is 13,000 tons of steel sitting in a jammed field of broken ice, with its hull gripped along both sides by friction and refrozen slush. So you go through the tools, and each one is aimed at a different part of the problem. The first is ramming, and it is exactly as crude as it sounds. The ship backs down along the channel it just made, builds speed forward, and drives the bow into the ice at a different point. Then it does it again. Depending on the thickness, this can take several attempts before the vessel gets through, and there are passages where a ship spends hours advancing its own length at a time. There is nothing sophisticated about it. It is momentum applied repeatedly to a surface that will eventually bend. The second tool is the one nobody outside the industry has heard of, and it is the most satisfying piece of engineering on the ship: heeling tanks. These are paired tanks on the port and starboard sides, and on a large icebreaker, each pair can hold in the region of 400 tons of water. Connecting them is a pipe of enormous diameter with pumps to match, and those pumps can move the entire contents from one side of the ship to the other in something like 15 seconds. What that does is roll the ship. Deliberately, hundreds of tons of water crossing the hull in a quarter of a minute heels the vessel hard over to one side, then the pumps reverse and it heels the other way. Repeat it and the ship rocks, on purpose, in a jammed ice field. And because the hull is wider at the top than at the bottom, that rocking motion pushes the surrounding ice outward and away, while simultaneously breaking the friction grip and any refrozen slush, holding the ship in place. A vessel that was stuck 5 minutes ago works itself free. It is a ship using its own ballast as a demolition tool. The third tool attacks the friction directly. An air bubbler system pushes compressed air out through holes in the lower part of the hull, and the rising curtain of bubbles loosens the ice against the plating and reduces the resistance of the ship moving through it. Some vessels use water instead. One Swedish icebreaker has 12 thrusters that spray jets of water onto the floe ahead, lubricating the surface so that a square bow and a flat bottom can ride up onto it more easily. The whole point of both systems is the sentence from earlier, applied backwards. Ice under 13,000 tons of pressure is not slippery, so you make it slippery. And then, on a modern vessel, there is the option of simply turning around and going at it stern first with the pods leading, which is why double-acting ships exist. None of it is elegant. All of it is a response to the same failure. The ship stopped moving, and the method requires movement. And there is a fifth option, which is not a tool at all. Sometimes none of it works. The ice is too thick, the rubble is too packed, the pressure in the field is closing the channel faster than the ship can open it, and the ramming is producing a ship's length an hour or less. At that point, the decision is no longer engineering. It is arithmetic. Fuel burned against distance made, with a convoy behind that is burning fuel too, and going nowhere. The answer is, sometimes to stop trying, hold position, and wait for the ice to move, because a pack that is under pressure today may be slack tomorrow when the wind turns. It is sometimes to call for a second, more powerful icebreaker and worth the same passage in company. And it is occasionally to accept that the route is closed, turn the convoy around, and take the long way. That last option is the one worth sitting with, because it explains something about how these ships are used. An icebreaker is not a machine that guarantees passage. It is a machine that makes passage probable, most of the time, in conditions where nothing else would move at all. And every crew working one knows that the difference between a 12-hour watch that covers 100 miles and a 12-hour watch that covers 11 is not skill or equipment. It is what the ice happened to be doing that night. Which leaves one question, and it is the one the whole night has been quietly asking. At 5:30, the sky on the port side is not black anymore, and the shaking has been continuous for 9.5 hours. Let us close the 4 things that we're trying to end this night. The ice was never the obstacle. A sheet fails easily under weight from above because sea ice is weak in bending. The broken ice was the obstacle, and the hull's flared cross-section, its wide beam, its propeller wash, its bubblers, and its jets are all answers to that one problem. The hull was never the vulnerable part. The propellers were, which is why the entire geometry of the vessel is arranged to route debris away from them, and why the most exposed component on the ship doubles as part of the system protecting it. And the ice was never the dangerous stretch of the voyage. The open water was, because every feature that made this hull capable in ice made it wretched in a sea. That is a genuinely elegant set of answers, and none of them is the reason this night went well. Because the thing this ship cannot design around is the fourth item, and it is the one you have been living inside since 8 in the evening. The crew is not exhausted by cold, the accommodation is heated, and the crew are professionals with proper clothing. They are exhausted by the fact that this ship has been shaking and roaring without pause for 9.5 hours, and it will shake and roar for the whole passage for days, and there is nowhere on board that is quiet. The constant jarring and shuddering of ice breaking under the hull, and the low continuous rumble underneath it, are conditions of employment. People who have done this work describe it in flat terms as mind-numbing. And they are not talking about the danger. They are talking about the noise, and it is worth being precise about why that matters, because it is easy to file it under discomfort and move on. Vibration and continuous noise do not simply make a person unhappy. They degrade sleep quality even when a person does sleep. They make it harder to hold a train of thought across a long interval, and they wear down the specific faculty that a night watch depends on most, which is sustained attention to something that is not changing. It is not hard to notice a ship stopping. It is hard at 4 in the morning in the 9th hour of a roar to notice that the ship has been slowing for the last 6 minutes rather than the last one, because the difference between those two readings is the difference between rolling the ship free and calling for a second icebreaker. So the watch rotates. People sleep in shifts they would not otherwise sleep in a bunk that is vibrating. And then they come up onto a bridge at 3 in the morning and make a judgment about whether to ram this flow or roll the ship free of it, and that judgment is the last component in the chain. The healing pumps do not decide to run. The pods do not decide which way to face. Nothing on this ship chooses when to stop trying and hold position for the night. Somebody with 9 hours of that noise in their head decides, and then does it again 40 minutes later, and again for the length of the passage. And when the light finally comes up and you can see the channel behind you, a black scar through white already narrowing with a line of cargo ships strung out inside it, holding station on your stern. The thing that got them through was not the steel in the ice belt or the hundreds of tons of shifting ballast. Those were available all night. What was scarce was the attention of the person choosing when to use them. It is worth remembering what that channel actually represents. Behind those cargo ships are ports, and behind the ports are the towns that get fuel, food, machinery, and building materials only when a hull like this one goes first. The route is not a convenience. For a good part of the year, it is the only route there is, and it exists because a ship deliberately built to be bad at being a ship went out and stood on the ice until it broke. Every winter, on every one of these passages, somebody takes the watch at 8 in the evening and does that for 12 hours, and the arrangement holds because they keep doing it. If this changed how you look at a ship that most people only ever see in a photograph, subscribe. This channel opens up the machines that make impossible work ordinary. Next time, one night at an Antarctic station at -60, where the thing most likely to kill everybody is not the cold, it is fire. And tell me in the comments, could you sleep through 9 hours of that?